This is the answer key for Chapter 8, Chemical Bonding. Write electron configuration for each element. Doesn't matter if you decide to use a long form or the shortcut form with a noble gas, as long as you put them in a bracket. Okay. For this one, we're gonna use a long one, and then find out valence electron. And notice that when you do the Lewis symbol, it's basically you draw element symbol, and you're gonna draw a dot for each of the valence electron. Na electron configuration is 1s2, 2s2, 2p6, 3s1. Notice the highest energy level in here is 3s, which has one electron in it, so therefore valence electron for Na is 1. Alright, so when you go to Al, you will see there is 1s2, 2s2, 2p6, 3s2, and 3p1. So you'll notice that 3s2 plus 3p1 together is going to give you valence electron on 3. Remember, your valence electron is highest energy level S and P electron added together. So the rest I follow. So for B, you're going to try to draw Lewis electron dot symbol. Notice that earlier we find valence electron for some of these elements, and notice all these elements come from level, energy level 3. So for instance, sodium, which we just did earlier, has one valence electron versus aluminum, which has 3 valence electron, right? So if you're gonna draw it, you're gonna draw 1 dot for sodium and 3 dot for aluminum. Should look like that. Notice that I decided to draw dot on the right side of sodium. It doesn't have to be on the right side. You can draw it on the top, you can draw it on the left side, or you can draw it on the bottom. As long as you draw only 1 dot by the sodium and a symbol, you get the correct Lewis energy dot symbol. Here is the rest of them. And notice that once you have full valence electron, afterward you start pairing them up. All right, Autek rule. Remember, we loosely in class set it as 8 valence electron, but we're not gonna use 8. So instead of 8 valence electron, let's think what should it say. When we say 8 valence electron, we're meaning to say it's actually 4 valence shell. Remember, S can hold 2 electrons and P can hold 6 electrons. So 2 plus 6, that's actually 8 valence electrons. So we're gonna try to say this without saying 8 in the definition. So the answer would be, it is just a tendency for atom to either gain, lose, or share electron until they are surrounded by a full valence shells. So they have electron around them that has full valence shell. Okay. 8.2 ionic bond. A, we're looking for Na plus versus Cl minus iron. So you have a picture of NaCl. Your job is to tell me which one is which one. And of course, we're going to try to explain it. So Na plus, notice at both Na and Cl actually originally from the 3, energy level 3. Right? Na has 3s1. Cl, the highest was 3p. Right? 3p5. Okay. So what's happening? To form Na plus, right? Na has to lose electron. So if it lose electron, that 3s electron, 3s1 is going to be gone. So it's the highest energy that you're going to have in Na plus is 2p6. So what is this happening? Well, 2p6 is closer toward a nucleus compared to 3p6, which is going to be formed by Cl minus, right? So because of that, Na plus is going to be smaller compared to Cl minus. Let's take a look. So again, what I just said, Na plus electron are in 2p, Cl minus are in 3p. 2p is lower energy than 3p, closer to the nucleus than 3p. So much more nuclear attraction there. So Na plus is going to be smaller than Cl minus. The smaller circles that you see in there are purple. So Na plus is purple. Cl minus is green in there. In this case, we're trying to draw an equation or represent an equation for how sodium atoms and chlorine atoms become sodium ion and chlorine ion. So we're going to use a Lewis dot structure to draw it. Here's an example, right? So sodium atom has one valence electron, so we draw one dot. Chlorine has 7, so we have 7 going around, okay? So notice what's going to happen. Sodium atoms is going to go ahead and give that electron to chlorine, okay? So remember, they want to have a 4 valent shells, so that's what they were trying to do. Sodium give away, chlorine gonna take it. So what's gonna happen now? Sodium gonna become plus. So remember, I think I lost an electron. You sure? I'm positive. Remember, losing electron is positive. Notice how I draw sodium Na plus ion as smaller than Na and Cl minus ion as bigger than Cl. That's because when atoms loses electron to form cation, cation are smaller than their original atom. Anion are generally bigger than their original atom. Okay, so this is partially on page 301, but you continue on to further pages. Let's talk about ionic bond. Okay, so first thing first, we know ionic bond is between a metal and non-metal, right? Right. Again, if you need to pause it, I will pause it so that you can write it down the answer. All right. Okay, so this is what we're talking about. So take a look, right? Stress is applied. It's gonna shift. What's gonna shift some? All right, this is interesting question. What happening when the sodium loses an electron? Okay, take a look. It did tell you what is this losing electron. Okay, first of all, you guys should know. That's all. Is there? All right. Number 6. If we combine two reactions shown above, so we'll combine that, we might think that formation of sodium is endothermic. Why is this view incorrect? Let's first try to do both. You will see here actually this. All right. G. Principal reasons ionic compound are stable is blank. Let's think. What is ionic substance? What did they do? Is between ion of blank charge. This can be examined with Coulomb law. Well, in the ionic compound, what's happening is positive ion attracted to negative ion. Okay, so that means it should say attraction between ion. Right? Principal reason ionic compound are stable is because there is an attraction between opposite charge there. Okay, which brings us to lattice energy. What is lattice energy? Lattice energy is the energy required to completely separate one molecule of solid ion into solid ionic compound into gaseous ion. So what does that mean? That's the energy to break apart NaCl. Okay, take a look at example. So here you'll see that we had two equations that exactly forward and backward of each other. So think about it. So the first equation is telling you Na, right? What we said, endothermic process, okay? Because you're breaking the bond. We already did this similar equation. All you will be is so MgO and NAF. If you remember your periodic table, by now you remember Mg is plus 2, O is minus 2, Na is plus 1, and F is minus 1. What does that mean? That means MgO is a clear winner because remember, greater charge, greater lattice energy. Okay. There is something else you need to know. What about size? If you think about size, you get a little bit confusing message for this one because Mg is slightly smaller than Na according to periodic table if you look at it, and also usually higher pluses are smaller than the other. Now if you look at the ion size, O2 minus is slightly larger than F minus 1. Doesn't quite make sense. Mg is smaller but O is larger, so unless you know the actual number, doesn't really matter much because based on the charges, we know MgO is gonna have the highest lattice energy. Okay, so check the charge first, then check the radius if you needed to, or if you need more evidence. Okay, please do not write down this one that about radius. All right, let's compare NAF and KCl. Okay, first of all, they are the same charges. All right, that means you're gonna compare them now. So when you're gonna compare them, the trick is compare cation to cation and anion to anion, because otherwise it's gonna create a mess. Okay, so if you look, Na is smaller than K, F is also smaller than Cl. So what does that mean? That means NaF is definitely smaller than KCl. Smaller distance, higher lattice energy. Okay, you just have to arrange them internal increasing lattice energy. First thing first, before you even do anything, you should notice. So you're gonna get something like that: KBr, LiCl, and MgCl2. Now on the test, if you have things, here's my reason between KBr, and then LiCl. So you can see, right? We're talking about internal size. Okay, MgCl2 and K and Li, it has to do with its charges. Right? Again, it's only Mg is 2 times, the rest are still the same, normal charging. So, greater charges, greater lattice energy. Alright. Okay, why can't we have Na plus 2? Because remember, greater charges is greater lattice energy. So, why don't we want that? Well, here's the thing though. Can we has Na plus 2? Let's see. Yes, kind of we can, but let's take a look. What is a valence electron of Na? We just did it earlier at the beginning of chapter 8. I think first few slides, you should be able to see it. Is because Na has one valence electron, right? So that means it can get rid of one electron and then the rest of the electron will be lower energy level. Because remember, the outermost shells only have one. So if you want to grab electron from inner shells, you need to spend more energy. How much more? Usually about 10 times. Now imagine that if they keep increasing every time, that's make it very, very difficult to remove electron consecutively. Okay. Okay. Na plus 1, right? After you lose it, so what's going to happen is to become Na plus 2. Remember, you're removing from inner energy level, inner shells, which really hard. Large amount of energy needed, even more so than lattice energy gained by Na plus 2. Okay, let's fill out this table. It's actually easy. You just have to figure out what each one is telling you. Na solid tend to Na gas. Straightforward. Okay, next one, ionization energy. Electron affinity of gaseous Cl atom. Electron affinity means when things gain electron. So in this case, Cl is going to gain an electron. So here's the equation that shows Cl gaining the electron. Okay, gaseous Cl atom gain, so it's become gaseous Cl minus ion. All right, so the last step is need is Na plus ion. Now gonna go ahead and combine with Cl minus 1 ion to form NaCl. Here's the equation that show that happening. By the way, that is gonna to be give you energy later called lattice energy, which you're gonna calculate in a later question. Write the balance equation for formation of NaCl. So you can see it's basically regular Na turn into Na and Cl turning into NaCl. Right, notice it's per mole here of NaCl present. So on this side, you should a little bit clear here. Okay, for this question, you're gonna be trying to calculate the lattice energy of sodium chloride, which is NaCl. We are using equation you see in O and P. First thing first, we write them up. Next, what you're gonna use is, remember when we did in net ionic equation, basically things on the left side of the equation can be canceled with the right side of the equation. So we're canceling the molecules or atoms or ions that you see on the left side with the right side. Okay, here is a result of me canceling out what you see on the left side and right side. So you can see that your total is pretty much the addition of the 5 equation above. Okay, so you can see the 5 equation added together is equal to the total. So that's all we did. And then solve for lattice energy. In transition metal, the electron is coming out of the valence shell first before they're gonna go to d orbital. The valence shells is gonna to be S for the transition metal. So remember, for the transition metal, they're gonna be losing electron. For instance, let's say they have 3s, 2, and then 2, well actually 4s2 and 3d, I don't know, 1 or something. You're gonna lose from 4s first before 3d. So here's an example. We're trying to write electron configuration for Fe2 plus. Remember, for Fe it's gonna be Ar shortcut. We're trying to write shortcut, so you're gonna say Ar, and then you're gonna have 4s2, 3d6, right? But for Fe2 plus, you're gonna lose s electron first, so you're gonna get Ar 3d6. Okay, but for Fe3 plus, you already lose this 4s, so you no longer have 4s, so you're gonna continue to lose from 3d, so therefore 3d5 for that one. All right, 3 type of bond. We kind of briefly did it today. Ionic, covalent, and metallic. Let's take a look at these two are hydrogen molecule. Where is a covalent bond? Remember, it should be in the middle. All right. notice the charge and where I'm drawing, right? Protons and electron floating around. Basically, in the middle of two protons is higher chance of electron being exist there. Right? In this case, this is the domain that he understanding. So, take a look at the next one. H2 molecule are held together because, well, they're held together because two positive nuclei are attracted to concentration of negative charge in between them. Right, so that's why you have a bunch more electron in middle. Or the name of the diatomic molecule. HNO F I HNO F ClBrI. I'm missing the F. You're just trying to write Lewis structure, diatomic. Make sure you count valence electron for both N before you draw N2. Same thing with O2 and F2. Valence electron, not just one, two, because you have two. Here's how you draw them. Notice we're following the out-type bonding. Bonding is draw with a line. Non-bonding is draw as a dot. All right, what's happening? We talked about this one before. I also show you in pictures. The more bonds you have, the more share pair electron you have, the length is gonna decrease. Okay, so this is seen here. Something else I want to quickly add to it, this chapter, right?